And we know from the work of the climatologists that with global warming, we're going to see winters warm a bit more than summers, and that nights will get a bit warmer than the days on average. They will warm a little bit more. And that northern latitudes, the Arctic, will be warming a little more than equatorial regions. In addition to changes in average temperature, we're going to see a lot of increases in extreme temperature events. In other words, heat waves. Although the term heat wave means different things to different people. If you talk to a climatologist or a meteorologist, they have a little different take on what the word heat wave means than somebody else. But just because the world's going to get warmer and we're going to have more heat waves doesn't mean we won't also have cold snaps as well. The key word here is we are anticipating a lot of variability increases. In addition to increases in average temperature, we'll see increases in variability. So weather is what we get, day-to-day variation in temperature, in sunshine and wind. Climate is based on long-term averages. So when you open up the newspaper in the morning and you look at, well, what's it supposed to be today based on the average? What's happening is NOAA, National Oceanic and Atmospheric Administration, calculates running averages from the last 30 years, and that's what they put in the newspaper. All right, so 30-year norms are what you read in the newspaper, and that's climate. So climate is what you expect, weather is what you get. All right? Well, you've all heard about global warming. What's that all about? Global warming happens because our atmosphere contains gases that intercept radiation from the sun and don't let all of that radiation bounce back out. So we have radiation that comes in, sunlight mostly, and infrared, and a lot of it is trapped in the atmosphere and can't bounce back out and comes back in and heats the atmosphere, just like a greenhouse, hence the term the greenhouse effect. There are lots of gases in the atmosphere that do this already. They're part of the natural Earth's ecosystem and Earth system in general. CO2, for example, has long been known to be a greenhouse gas. It absorbs heat. And that principle is used, in fact, to measure CO2 in instruments. Water absorbs heat. So the more water in the atmosphere, the more heat is absorbed. So there are a number of major greenhouse gases that are already there. They already do the job of absorbing heat. But in addition, we add a few new ones to the mix sometimes, human beings, and we increase the levels of certain greenhouse gases that already exist. Most of the warming that's taking place now that's driven by human activities is associated with this particular gas, carbon dioxide, CO2. Although there are others involved, CO2 accounts for about 2/3 of the problem. The other third is driven by methane and some other gases that I'll talk about in a minute. But the main culprit is CO2, and CO2 is mostly coming from the burning of fossil fuel. So think about it. When we pull up coal and oil from the ground, that is carbon, partially decomposed living bodies of plants and algae and bacteria from long ago, millions of years. And that carbon is organic carbon, and we burn it. And so that carbon is then converted to CO2 and released to the atmosphere. So now we've pulled up a reservoir of carbon that wasn't in play, that wasn't part of the Earth's carbon cycle. And now we're injecting that new carbon into the Earth's carbon cycle. All right? And we've increased the levels of CO2 in our atmosphere by about 43% since the dawn of the industrial age. And I'll show you some data that show you how fast CO2 levels in the atmosphere are going up. Water vapor is a greenhouse gas, a potent one. Methane is a potent greenhouse gas. In fact, pound for pound, it's about 25 times more powerful than CO2. All right? And we're increasing methane concentrations in the atmosphere through human activity. Nitrous oxide that comes from the burning of fossil fuels is a greenhouse gas, and it also contributes to things like acid rain. Tropospheric ozone, the ozone that's close to ground level, is a greenhouse gas, as are a few other compounds that we emit, produce, and release to the atmosphere. But CO2 and water vapor and methane and a little bit nitrous oxide, those are the real biggies that are contributing to global warming. We can go back in time through various means and make direct measurements of carbon dioxide in the atmosphere, trapping. We can measure CO2 that was trapped in ice. We can measure CO2 that's found in wood, for example. So we can go back about 1,000 years here of more or less direct measurements or direct proxies, if you will, and ask what was the CO2 concentration in the year 1000, for example, here, and follow it forward to the year 2000. Here's carbon dioxide. You can see, if you can't read the numbers in the back, that on the left we have the year 1000. And here we have the year 2000. You'll notice we have a flat line. CO2 concentrations in the atmosphere were stable around 280 parts per million. Doesn't sound like very much, but it doesn't take much to warm the atmosphere. And then you'll notice about 1860, 1870, CO2 in the atmosphere starts to go up. What happened around 1850, 60, 70? The industrial age began. We learned to burn oil and coal at a very rapid clip. And we had an almost immediate impact on the levels of CO2 concentration in the atmosphere. But CO2 is not the only greenhouse gas that's been going up. Here's nitrous oxide, methane, and all three of those are potent greenhouse gases. They've all been going up since about the dawn of the industrial age. They're all linked, all right? If we were to zero in, scientists began to notice that CO2 concentration was going up in the atmosphere around the 1950s. There was a scientist and his graduate students that were making measurements in the Hawaiian Islands, atmospheric CO2 levels, because they thought, we're far from the mainland and industrial activity, and we should be able to see very clean air. And so get a very good measure of the baseline CO2 concentrations in our atmosphere. And they started to take measurements, and in just a few years, they noticed that CO2 levels were beginning to creep up in the atmosphere. And this is the so-called Keeling Curve that's oftentimes referred to. But notice it zigzags. That's summer and winter in the northern hemisphere. That's photosynthesis. So in the springtime, the trees wake up, they start to do photosynthesis, and they pull CO2 out of the atmosphere and lock it away in plant growth. And then in the fall, the leaves fall and they decompose. In the winter, that CO2 goes back up. Just goes to show you how important plant vegetation is in global photosynthesis in terms of CO2. All right, but CO2 is going up, and now, just a few months ago, we crested 400 parts per million. So that curve that I just showed you is out of date. Most of this CO2 comes from power plants and automobiles, coal and oil, all right? And until recently, the worst culprit was us. And a few years ago, we've been surpassed by China in terms of CO2 emissions. But most of the CO2 that's up in the atmosphere right now that's causing problems, we are to blame. Here's a look at the global carbon budget using a slide I pulled from the BBC. British Broadcasting Corporation does really wonderful coverage of general science. And if you want to look at science coverage that's put in a really good way for the general population, take a look at the BBC. I come in every morning to my office before I teach, and I look at the BBC website, and I pull articles off the website and take them into class. So here's one of their slides. What we have in this slide is the global carbon budget, and the arrows are fluxes, where we're having movement of CO2 from one compartment to the next. And the compartments are in red circles. And the size of the red circles tells you proportionally, how much carbon is in that particular compartment. So here we have a giant red circle, that's the ocean. Lots of carbon is tied up in the ocean. And here's the atmosphere. Not so much carbon in the atmosphere. And then we have CO2 that comes out of the ocean up into the atmosphere, and CO2 that comes down. And these two fluxes are more or less balanced. All right, that is about the same amount comes out as goes back in. Over here we have here's a circle here that has vegetation, all the plants on the planet. If you add up all the grams of plants, you can calculate how much carbon do we have in plants. And those plants do photosynthesis in the summertime, so they pull carbon out of the atmosphere. In the wintertime, they die and they decompose, and that carbon goes back up. And these two arrows are about the same size. So what's set off an increase in CO2 concentration in the atmosphere is we have this new flux that doesn't have a balance arrow. And that new flux is carbon that was tied up in coal and oil. And we're burning that and releasing it to the atmosphere, and it goes up into the air, and there's no other process to pull it out right now. It is increasing the rate of plant growth, so plant growth is increasing a bit, but it's kind of like a drop in the ocean. It's not going to be enough to slow down the increase in CO2 concentration in the atmosphere and to slow down global warming.